This is probably the most difficult thing we've done so far, the stuff we're working on today. It's why I put it off and didn't do it right before the testing, because I thought, ooh, I am not going to give you guys this and then take off for a week. In a way, it's all stuff that you have done before. We're simplifying trig expressions. We're going to use our identities to help us break things down. A lot of what we've done with other things, like we've done it with quadratic equations and stuff like that. And the processes are the same, but it'll be weird for you to see it with trigonomic expressions, and that might make it seem a little bit confusing. And so that's why I wanted to take time with it. I didn't want to jump into it and then leave you guys hanging for a week. If you remember the last time I saw you, we were dealing with trig expressions as well, and we were doing the parts where I believe we were just like evaluating trigonomic expressions, right? We were using the fundamental identities to evaluate and find solutions. And today we're going to talk about simplifying trigonomic expressions and factoring trigonomic expressions, and then a little bit of adding them. So here's the thing. When we're talking about simplifying or factoring something, simplifying always means we're going to make it as small as we possibly can. We're going to write it in its simplest form. Factoring, we're making it as big as we can. We're taking all the components out of it and breaking them down. So think about it in that respect. Simplifying means making it smaller. Factoring, we're making it bigger. All right. And today we're going to be starting with simplifying. And notice I have the trig identities up here, and I'm going to move them along the board with us. Why? Because it'll help us to be able to see these things in front of us while we're working in it. And so we're starting with simplifying trig expressions. It's trigonometric, but that's a long word. So is expression. So we're going to leave it like that. When we're simplifying trig expressions, like I said, simplifying means we are making things smaller. And I hate the new whiteboard. So if I have sine of x times cosine squared of x minus, let's make that a prettier minus sine of x. And it says simplify this expression. I need to look at this and think, first of all, what can I do to it? When I look at this, I see that we have, right here, we have a sine on this side and a sine x on this side. So I think I'm going to factor out sine of x. Right? They each have it on each side of that minus sign. We have a sine of x. So why don't I take it out, right? I'm going to go, okay, well, if I pull sine of x out, if I pull it out of this side, I'm just left with cosine squared of x minus, well, if I pull it out of this side, sine of x divided by sine of x is just 1. And so I wind up with this little thing. Well, if you notice, this cosine squared of x minus 1 is fairly similar to one of these Pythagorean identities, right? Like if I were to write this, if I were to move this cosine over, I would have 1 minus cosine squared of x, right? If you see that over here, right? If I moved this over, I could do that. And how would I make this look like that? Well, I go, okay, well, if I just subtract out, if I factor out a negative, that's going to work, right? So if I make this negative sine of x and factor out a negative just like I did here, this would become minus cosine squared of x plus 1, right? And we can write that any way we want. We could go, okay, well, that's minus sine of x times 1 minus cosine squared of x. And we know that that is the Pythagorean identity. We know that sine squared of x equals 1 minus cosine squared of x, right? That's that Pythagorean identity. And so I can say that this is just sine. So I wind up with minus sine of x times sine of x, which is just going to equal negative sine, this is sine squared of x, right? Which is going to be negative sine cubed of x, right? And we use the Pythagorean identity to find that. And there's all sorts of problems that we could do that would work similarly to something like that, right? If I had, as another example, cosine squared of x times cosecant of x minus cosecant of x, and I asked you to simplify it following the same pattern that we just did. What could I factor out of both sides? What does both sides have in common? It's going to be a long video. Thank you. Both sides have cosecant in common. Thank you, Moises. I appreciate that. Which means I can take cosecant out of both sides. I can rewrite this as cosecant of x, right? Well, if I factor it out of this piece right here, I'm just left with cosine squared of x. If I factor it out of this piece right here, well, cosecant x divided by cosecant of x is just 1. Looks familiar to up here, does it not? This one works out, I think, a little bit prettier. I don't even need to redo this one, right? We know that if I factor a negative out of this one now, and I have negative cosecant of x, this winds up being sine squared, right? If I rewrite this, I factor out the negative and I wind up with 1 minus cosine squared x. We know that that is sine squared. And so right now I have minus cosecant of x times sine squared x, right? Why? Because of the Pythagorean identity, just like we did in the last bit. Now, this isn't completely simplified because if we look at our chart, we can also see that sine of theta is equal to 1 over cosecant of theta. And in retrospect, we could say that cosecant of theta equals 1 over sine of theta. So ultimately, what we have here is negative 1 over sine of x times sine squared of x, right? Which is going to give us negative sine squared of x over sine of x. Does anybody know what that would equal? If I have sine squared of x over sine of x, what would I wind up with? Think about this. If I have x squared over x, what does that equal? If I have two x's on top and I have one on the bottom, right? This one cancels out one of these, and I'm just left with x. The same thing happens here. I have 2 sine x's on top, and I have 1 on the bottom. So this is going to cancel out one of these, and I'm going to be left with negative sine of x. Make some sense? Trying to swallow it, a lot for 8 a.m., 8:20 in the morning, right? And that's what we're looking at when we're talking about simplifying, right? We're trying to make it as compact as possible. We just went on this. Ooh, I hate it when that happens. We just went from this whole mess right here down to negative sine x. They're equal. They're the same thing, right? And we just broke it all down. Now we're going to talk about factoring. Factoring, when we're factoring these expressions, we're making them bigger, right? We're breaking them down to their parts. So if I have, for example, I almost wrote the same example I just did. If I have secant squared x minus 1, and I ask you to factor that expression, we have to start thinking about things a little differently and pay particular attention to this problem and the next example that I use, because the ones in your homework are going to be similar to this. All right. So when we're factoring trig expressions, what I see here is I have a perfect square, right? How do I know it's a perfect square? It's squared. Minus another perfect square. How do I know it's a perfect square? Because it's 1. 1 is always a perfect square, right? And with that minus in between them, what I know is that I have what we call a difference of squares. And we went over this last semester. You went over this in Algebra 2. You've done this in Algebra 1. But when I have something that's a difference of squares, if I have, say, x squared minus 1, I can rewrite that as x plus 1 times x minus 1. And I know this because it's a difference of squares. We've proven it on many occasions. At this point, you're just going to have to take my word for it, right? So what I know about this is that if I have a perfect square minus a perfect square, I can write this now as secant. I don't know why I keep wanting to put that x there. It's not what I don't want to be writing sex. I want to be writing secant of x. I could take secant of x minus 1 times secant of x plus 1. Is that completely factored? Yes, it is. Right? I can't factor that down any more than I can factor down x squared minus 1 more than x plus 1 times x minus 1. That's as factored as that's going to get for me. Is it always going to be that not work heavy? No. Sometimes you're going to have to do a little more. I mean, sometimes you could wind up having to do like a quadratic formula or something on that. I don't believe you have any homework problems that are going to take you that deep into it. But I will do another example here. If I have 4 times tangent squared of theta plus tangent of theta minus 3. When I look at a problem like this and I want to factor it, the tangents throw me off. So I like to think of this problem as if I make tangent theta equal to x, I could rewrite this problem as 4x squared plus x minus 3. And it makes it a little easier for me to put into perspective, right? When I'm solving a problem like this, I like to try and look at it in x's instead of tangents because they're going to solve the same way. And so if I was factoring this, everyone's got their own way of doing these kind of factors. Some of you guys use like that X method. The method that I use and that I used with you guys earlier this year is that I multiply these two terms together and I rewrite the problem as x squared plus x minus 12. Do you guys remember this? Let me finish this problem, David, and then I will. Do you guys remember seeing problems like this? This is quadratics. You learn about them. And okay. So now when I factor this, I know that here I would have x plus something times x minus something. And the reason I know that is because I have a negative at the end. And we're going to look at our factors of 12 that would add up to 1. And if I look at 12, I'm going to go, okay, well, my bigger factor is positive. So I'd have negative 1 and 12. I'd have negative 2 and 6. I'd have negative 3 and 4. And look, if I add these two together, I'm left with 1. So those two work. So this would be 3 and this would be 4. And I can't leave it like this because I did multiply that 4 in the beginning, which means I have to divide it out in the end. So I'm going to divide by 4 here and divide by 4 here. If it divides evenly, right, which it does here, 4 divided by 4 is 1. So this becomes x plus 1. If it doesn't divide evenly, like in this case, 3/4 does not, 3 divided by 4 doesn't give me an even number. And if it doesn't, we're just going to move this 4 out in front of the x. So that would be 4x minus 3. Now this is our factored final problem. So factoring, we get bigger. Simplifying, we get smaller. I'm going to roll this up here a little bit for David. Is this the problem you needed to see, David, or the one before it? So I can get them both on here. De nada. You good now? Okay. I had some more factoring and simplifying problems and adding, but we don't have a ton of time. So I'm going to do an addition problem, and then later today I'll make a little video with just some extra sample problems, okay? So I have some more simplifying stuff to show you and some more factoring stuff to show you just as examples, but I'll put them on a separate video and we'll go over adding and be done with that today. When we are adding or subtracting trig functions, mostly in terms of in a fraction form. So if I have, for example, 1 over 1 plus sine of x plus 1 over 1 minus sine of x. When you're adding fractions, what is the one thing that you need to have to add any fraction? Don't think of it in terms of what you're seeing here. If I'm adding a fraction or subtracting a fraction, what do I have to have? If I have 1/2 and I want to add it to 1/3, what do I need? What do I need to find to make those things happen? Yeah, common denominator, right? I can't add 1/2 to 1/3. The denominators have to be the same. So on this piece, I would multiply times 2 over 2. And this piece, I'd multiply 3 over 3. And we would wind up with, oops, sorry, I got that backwards. This I'd multiply times 3 over 3. This I'd multiply times 2 over 2, right? And here we would have 3/6 plus 2/6. And then we could add them together because they have the same bottom, and we would have 5/6, right? Well, the same thing is true when we're dealing with trigonometric functions, right? We still need to have a common denominator to add any kind of fraction or subtract any kind of fraction. So when I look at this, I go, okay, well, here we have 1 plus sine of x, and here we have 1 minus sine of x, right? So what I can do to make these denominators common is erase all this stuff I just did, is I can multiply both sides by what the other side doesn't have, right? So this is 1 plus sine x. This is 1 minus sine x. So if I multiply this side times 1 minus sine x over 1 minus sine x, and then I multiply this side by what it doesn't have, which is 1 plus sine x, 1 plus sine x over 1 plus sine of x. I can now add these things together. Now, if you look at this problem, if I multiply 1 minus sine x times 1, I'm just left with 1 minus sine of x, right? And it's all going to be over. I'm not even going to multiply these together. I'm just going to go 1 minus sine of x times 1 plus sine of x, right? Now, if I look at this side, if I multiply 1 times 1 plus sine x, I'm left with just 1 plus sine of x, right? Because anytime I multiply anything times 1, I'm left with itself over, same thing, right? We're going to have 1 minus sine of x times 1 plus sine of x, which means that we can just add these top pieces together, right? Well, I've got 1 plus 1. Well, that's 2. And I have minus sine x plus sine x. Well, those cancel each other out. So here I'm going to be left with 2 over 1 minus sine of x times 1 plus sine of x. I feel like we can do better than that, right? Can we do better than that? If I multiply these two things together, let's look at what we get, right? It's going to be something with 2 on top, right? We're going to have 2 over something. What are we going to have? We're going to have 1 times 1. Well, that's just 1. We're going to have 1 times sine x. Well, that's sine x, right? Plus sine of x. We multiplied that 1 times everything. So now we're going to go minus sine x times 1. Well, that's minus sine of x. Look, those are going to cancel. Then I'm going to go minus sine x times sine x is going to give me minus sine of square root of x. These are going to cancel, right? Sine x minus sine x just cancels. So now I have 2 over 1 minus sine squared of x. Well, if we look at our Pythagorean identities, we know that this piece equals cosine squared of x. So we have 2 over cosine squared of x. Now, you get this far. We're like, yeah, awesome, but we're not there yet. Because anything over cosine of x equals secant, right? Where do we have it? Right there. 1 over cosine squared of x equals secant. So I can write this as 2 times secant squared of x. That would be my final answer. How do you get to these? Well, you fail. Like you do it and you mess it up and you look for another way. Are you always going to get there right away? No. These are work heavy problems, right? They're labor intensive because if you don't see it right away, it's going to be hard for you to get there. And it's one of the reasons I didn't want to leave you hanging on it, because these things take practice and they take looking at this little chart right here and trying to figure out, well, how does this fit with the other? For a lot of you, I know you'll look up the answers, but try and play with these. They're little puzzles. I think you can get them. I will have a few more sample problems that I'll do for you on the video, but I want to stop this one because we only have a few minutes left, and I'd like to open that up to see if you guys have any questions about any of it, or if there's just so much you're like, I don't even know what questions to ask. So I'm going to stop the video. You guys let me know if you have any questions. Pop them into the box, and we'll get into it.